Welcome to YouTube video lecture for the physics, fundamental of physics. I believe you are getting benefit from my video lectures. If you are looking at, thank you for watching. Please subscribe to the channel, like it if you like it, and turn on the notification. Press the bell icon so that you get quick notification whenever I upload new videos, and share it with your friends so that everyone should get the benefit from these lectures. And don't forget to give me your feedback to improve these lectures. Today we are going to start chapter number 19, magnetism. If you look at this animation, the title slide of this chapter, the cosmic rays, the charged particles coming from space to the earth, so they interact with the earth's magnetic field and give rise to the lights. Near the magnetic north pole, the lights so created are called the northern lights or the aurora borealis, and near the southern magnetic pole, the lights are called the southern lights. What we'll be doing today, the topics, first of all, whenever you have magnetic field and a charged particle is moving and enters into magnetic field, what force, magnitude and direction that charge experiences we'll discuss. And then similarly, if you have a current carrying conductor where many charges are the moving within the conductor, we will be discussing magnetic force on a current carrying conductor, a piece of wire. Then magnetic field of a long wire, and we will discuss the Ampere's law. So, basic concepts, as you know, that you might have been experiences magnets since your childhood. You know that it has two poles, north and south pole. Okay, magnets come in pairs, no monopoles. You have discussed in electrostatic, chapter number 15, that you may have a single positive charge, and due to that you have an electric field. You may have a single negative charge, you may have electric field around that charge. But keep in mind, in magnets, they are always present as a pair, north and south pole, not a single north or not a single south pole. Keep in mind. Even if you keep on breaking into smaller pieces a magnet, still it will be having one north and one south pole. And the electric charges, force lines you have already, and the field line you have discussed. Now if you have, for example, one magnet here, first of all keep in mind that the magnetic field lines go out of the north pole and enter into the south pole. If you have two magnets here, north of one, near to the south of other, so you know that like poles repel each other. If you have both north, both south, they will repel each other. And unlike poles, like one north, one south, they will attract each other. So there is attraction here. I'm going to show it with the magnetic field lines. You see, out of the north pole into the south. This is what we learned in the beginning, right? Out of north into south. So this is how we can show the magnetic field lines. Earth magnetic field. Earth, as we know, that we have many molten metals flowing with very high speed within the crust of the earth, giving rise to the current, right? So due to that current, we have magnetic field. So earth itself is a big magnet. And you know, once we say that this is the north pole or the south pole of a magnet, so in fact that north pole is looking for the south. As I told you, the unlike poles attract each other. North will attract the south. So once we talk about the north pole, it means it is seeking the south pole, so that it will be having attraction. So a south magnetic pole is near the Earth's north pole. So magnetic north, magnetic south near the north of the geographic pole, right? So this is here, south geographic pole and magnetic pole north. So this is how they attract each other. And as I told you, Earth itself is a big magnet. Now, let's come to the actual topic. As I told you that we are going to calculate the magnitude of the force, magnetic force we call it, because it is due to the magnet. So magnetic force F on a charge Q moving with velocity V in magnetic field B. You might have done in chapter number 3 vectors and the cross product of vector. If you remember, you did it, A vector cross B vector is equal to some other vector C, and its magnitude we did AB sine theta. This is the magnitude and direction by a right hand rule. Right. So we have here V. You see, for example, if you have two magnets, as I told you earlier, you have from the north into the south pole, these are the magnetic field lines. So you have magnetic field here, magnitude B. If a charged particle is traveling, with velocity V, when it enters in the magnetic field, keep one thing in mind, that whenever you have moving charge, we have done in chapter number 17, Ohm's law and the current and resistance, that moving charges mean current electricity. So whenever you have electric current, you have magnetic field around that conductor or even the moving charge, right? So we have two magnetic fields now. One magnetic field you already built here due to permanent magnet or even the electromagnet. This one magnetic field, and when the charge is moving, so moving charge means current. So due to current, we always have magnetic field around that. So we have two magnetic fields. So due to interaction of these two magnetic fields, one due to this permanent magnet and the second due to the moving charge, this interaction of the two magnetic fields has an interesting result. What is that result? The result is that this charge will experience a magnetic force. So this is the magnetic force F or FB, or sometimes you may have seen it FM, M for magnetic force, or B due to magnetic field, this one. So this is A cross B, AB sine theta. Now you have this magnitude, these are the vectors. So if I talk about the magnitude, so Q V B sine theta, right? Whereas as I told you, B is the magnetic field, F is the force, Q is the charge, V is the velocity, and theta is the angle between the two, between V and B. For example, this is V and this is B. this is theta. Right. So let's talk about, if I need magnetic field B from this equation, I would get like this one. So B is equal to, I take QV sine theta down, QV sine theta here in the denominator. So magnetic field B is equal to force divided by QV sine theta. Now let's decide the unit. Force, Newton. Charge in coulomb. Velocity in meter per second. Okay. Now we have coulomb per charge per unit time, that is current. So charge per coulomb per second is ampere. So Newton, ampere, and meter. We call it Weber per meter square also. We have a smaller unit, we call it Gauss. 1 Tesla is equal to 10 to the power 4 Gauss. So this is called 1 Tesla. Tesla is the SI unit. We have some conventional units also like Gauss and the Weber per meter square, but SI unit is always Tesla. If you are given millitesla, you have to convert it into Tesla. Now, this is one thing interesting. You will be looking and considering this in many examples. For example, if you have this board, you have two magnets, right? One magnet here, one after this wall, right? And you have this from the north of one, this south of the other. So magnetic field lines will be into the board. For into, we use cross symbol. When you see cross, it means it is into. And if you have this one magnet, for example, this is south, this is north, and this is south of the other and the north of the other. So from the north to the south, out of. So once the magnetic field is out of direction, so we use dot. So dot for the out of, cross for into. Keep in mind. Right. Now, that was the magnitude, right, of the magnetic force on a charge. Keep in mind, this force is due to for a positive charge. Okay. Now, for the direction. Okay. For the direction of force on the charge. So keep in mind this right hand rule, we call it right hand rule number 1. Right hand rule number 1 we call it. Okay, so right hand rule number 1 to find out the direction of the force on the positive charge when it is traveling in the magnetic field. So what is the rule? The rule says if you think that this is the velocity, the positive charge is moving in this direction, and this is the direction of the magnetic field. So move your right hand from the first vector V, velocity, to magnetic field B. In this case, it is up, right? Actually, we have to have three, dimensional, like this one. For example, if I asked you to take this is the one corner of the room, for example. I take this x-axis, this y-axis, and this z-axis, right? Now, if your velocity is here and magnetic field is here, so from velocity to magnetic field, this is velocity, this is magnetic field. From velocity to magnetic field, up is the direction for the magnetic force on the charge. Right, so this is how we do it. Again, right hand rule number one. Okay, right hand rule number one for determining the direction of the magnetic force on a positive charge moving with a velocity v in the magnetic field. These four fingers in the direction of velocity to this gives the direction. For example, if they are in the opposite direction, so we have to move our hands similarly in the given way. This is for the positive charge. What about the force on the negative charge in the magnetic field? If you are given a negative charge, first do it for the positive charge, but since it is negative, finally you can reverse the direction of the force. For example, if you are given this negative charge now, for the positive charge you see force up. For negative charge, reverse the direction. Simply. Alright. Let's use our knowledge we just finished. Yes, you have, first of all, we just finished magnetic field Q, V, B, sine, theta. Just a little review before we go further. For example, if you have theta 0, mean velocity and magnetic field, they are in the same direction. And sine 0 is 0, so force will be 0. And if theta is 90 degree, sine 90 is equal to 1. So the force will be maximum. Right? QVB. Okay, this is how we can interpret. Okay, let's go to this example. Right. You have a proton. Proton is a positive charge. Okay. So keep in mind once you are going to find the direction. So this is for the right hand rule is for the positive. For the negative you reverse finally. But here no problem. Q is given, moves with a velocity meter per second through Earth's magnetic field, which has a value of this. B is given to you. Micro means 10 raised to power minus 6 at a particular location. When the proton moves eastward, you see eastward. So this is V. Okay, towards east. Moves eastward, the magnetic force acting on is upward. So two things are given. This is given and force is given up. This is not north, this is up direction. Keep in mind. I will explain it shortly. And when it moves northward, no magnetic force acts on it. Okay, what is the direction of the magnetic field? B. Okay, magnetic field B direction. You have to find out A part. I think if I say east, west, north, south, the students, they are confused with this north and up direction. So you see we have 6 directions: east, west, north, south, and up and down. I think I will give you this idea Give me 1 second, please. Okay. Okay, give me 1 minute. Okay. You have this one. Yes, it's good. You see, first of all, I'm standing here. Okay? East, west, horizontal, north and south. Okay? East, west, north and south. Up and down. Again. Look, can you see this east? This horizontal east. This is west. Okay? This is north. And this is south. And this is up. And this is down. East, west, north, south, up and down. I think you better take the idea now. Okay? So keep in mind, velocity is given. Which direction? East. This direction, velocity. And I have to use right hand rule number 1 without changing the given directions. Velocity in this direction. And force is up. This is force. Okay? Force is up. So this is your force now. Okay? Let me write it here for you. This is force. Force is up. And this is your what? V. Okay? So, right hand rule, from velocity, this is force up given. If I take my right hand rule, this, it will be wrong because thumb is, force is here, but force is given up. I cannot even keep my hand like this one. Okay? Because force is not, but force is given up. So from east, velocity, from velocity, I cannot move my hand like this one. That would be wrong. So right hand rule number 1 says, from velocity to this. And you have 3 vectors. Velocity, force, and magnetic field. Any 2 directions given, you can find out the third one. So what is the case here? You are given velocity and force direction. You have to find out magnetic field direction. So from velocity to here, up force. So your magnetic field must be north. So magnetic field is north. So done. So this is north by right hand rule number 1. Clear? Alright. Now, the magnitude of the force. Okay. You see, as I told you, this is, velocity and this is magnetic field north. So what is the angle? 90 degree. So theta is 90 degree. So magnetic force F or Fm or Fb same. QVB sine theta. It's given. Okay, velocity given. Magnetic field given 55. Keep in mind, always convert in SI units. As I told you, SI unit for magnetic field is Tesla. So micro 10 raised to power minus 6. Theta 90 between velocity in the east and magnetic field in the north. So 90 degree. Sine 90, which will be 1 by the way. Okay. Now, okay, so you get the magnetic force on the positive charge. Yes, 8.80 into 10 raised to power minus 19 Newton. That's it. Then C pot. part says calculate the gravitational force, which is given by gravitational force is given by mass of the charged particle multiplied with the gravity, expression due to gravity, and the electric force. Electric force is given by, you know, Q multiplied by E. We have done in chapter number 15. So the mass of the proton is given to you 1.67, 9.8. You would get 1.64 minus 26. And gravitational electric force, E is given to you. So Q is given to you 1.6. E is given to you 1.50. So you get electrostatic or electric force. It will be 2.4 10 to the power minus 17. Okay. So if you compare all these forces, you see the magnetic force is in part B 10 to the minus 19. This is electric force. Okay. And this is your gravitational force. All right. Now, next question, please. Right, so this is the next question, A part. You have a proton, charge on the proton is given, mass of the proton is given, moves. This is the velocity of the proton, of course, positive charge along the x-axis. So x-axis is the velocity. Think three-dimensional coordinates. X, Y, and Z axis. So x-axis, along x-axis, the charge is moving, the positive charge, so velocity. It enters the region in which there is a magnetic field. B is equal to 2.5 Tesla, directed at an angle of 60 degrees with the x-axis lying in the xy plane. So this is x-axis, this is y. So this is xy plane, 60 degrees from x-axis towards y. Find the initial magnitude and direction of magnetic force. So magnetic force, you have to find out. A part of the question. Alright. So, first of all, direction. Right? You see, if you take the room has four corners, right? Now, think about one corner of the room. This is the corner of the room. This is one wall. This is the other wall. Now, I take this from, this is the origin, 0, 0. Okay? Origin point. This is x-axis where you have velocity. This side. Okay? And this side, y-axis, this is z-axis. So, from the x-axis 60 degree is your magnetic field B here. Better you can understand from here. This is x-axis, this is y-axis, the height is z-axis, okay? The corner of the room. So from the velocity to magnetic field, which is 60 degree from x-axis, okay, direction will be from v velocity to magnetic field, which is 60 degree from x-axis. This term will give you the direction of the force, which is along z-axis. Okay, positive z-axis. Okay, this is V, and that's it. So direction of force is about positive z-axis. Done. Now for the magnitude of the force, we have sine theta. Q is given, velocity is given, magnetic field sine of 60 degree. You would get the magnitude 2.77 times minus 12 Newton. Okay. Now, B part of the question. Calculate the acceleration of the proton's initial acceleration. You know, we have Newton's second law of motion, F is equal to ma, so it would give you A is equal to force, which is magnetic force, of course, or the mass. Force, the mass of the proton so you would get the acceleration 1.66 into 10 to 15 meter per second square. Okay, keep this lecture up to here. See you the second part of this shortly in the second part of this the next topics in the second part of this chapter, inshallah, shortly. Okay, and thank you very much and have a nice day.